Hey guys, welcome. Yeah, so first as always, thank you, Lord Christ. I love you. You're amazing. Yeah. And second is I have a bonus example here on mathematical induction. Now, I have several videos on mathematical induction, anywhere from like showing you how to prove the formula for the sum of the cubes of the integers, so a very typical induction proof, to divisibility and inequalities, and we even use induction to prove the number of subsets of a set with n elements. So why another video on induction? Because this is a unique one. This is different, and therefore you'll get something different out of it. Yeah? Okay, cool. Now, one of you in a comment said about IVHL math, which is where this question comes from, that it's not rigorous. First of all, where else in high school math do students do proofs like this? IVHL math. And so it is rigorous, the IB education. Also, I guess the point is that like it's all relative. Like what's hard is relative, and that's the point that the person made, which is that like, well, it's just that these proofs are like presented to high schoolers. Yeah, so that's what makes it rigorous. Because otherwise, like nothing is rigorous, right? Like everything is hard only insofar as you haven't been taught it well and you haven't practiced it. If you practice something enough times and you've learned it the right way, then nothing is hard, right? And so hopefully I make this easy. Let's go. All right, so at the heart of understanding the proof that we're gonna write here is knowing that if I have sine, right? If I have sine and I go sine of theta plus pi over 2, notice this is a transformation of sine. Specifically, it's a shift of sine to the left by pi over 2. But wait, graph sine, shift it to the left by pi over 2, and see that it's going to equal exactly cosine, right? So it's going to be cosine theta. All right, so need to know this. Keep this with you in this video. If you do not keep this with you in this video, you will be lost. You will not understand this proof. Yeah? Okay, enough said. Let's get on with it. As usual, we start our induction proof with the first case. Case n equals 1, right? And it should go without saying, but this here is talking about the nth derivative. So you have the function f, and fn is the nth derivative. So when n is equal to 1, we're talking about the first derivative. Well, that would be f prime of x, and that clearly is equal to a cosine ax. Fine. If we let n equal 1 here, do we get that? Well, yeah. So f1, so the first derivative, this time I wrote a 1 as opposed to a prime, but same thing, of x is going to be, well, according to this formula, it's going to be a to the first, right? And then sine of ax plus n is 1, so plus pi over 2. Remember what I told you? So if we get rid of this, because we don't need that, then the rest of it says sine of theta plus pi over 2. I'm calling theta ax here. So we've got sine of theta plus pi over 2. Remember what we said that was? We said that was cosine of theta. So we write a cosine of ax. D'accord. They're in agreement. This is the same as that. Okay, case 1 complete. Got it. Now, the next case is case n equals k. Case n equals k. We know that this is an important case. In fact, so important that it's called the inductive step, but you don't actually do anything in the inductive step. It's just that you replace the n's with k. So that I don't have to do so much writing, I'm going to just, I'm being lazy. It's not a lot of writing, but I'll just replace the n's with k here, and remember the qualifier that n was an integer and k is also an integer. So here we are, specifically positive integer. Okay, cool. So this is the inductive step. So again, it's called the inductive step. It's of great importance, but you don't actually do anything other than change the n's into k. So why is it important? Because it must always come into play in the next and final step. So the inductive step has to be used somehow in the final step. Got it. So we know we're going to somehow use this in the final step. What's the final step? Well, the final step is case n equals k plus 1. Okay, cool. So then what we're going to say is, if we use the formula, right, we're going to say f k plus 1 of x, the k plus first derivative, is going to equal, by the formula, and I've written the formula part on in red, so let me do that. Let me do it in red. So we're going to say that it's f k plus 1, by using the formula, is going to be a to the k plus 1 sine of ax plus k plus 1 pi over 2. Obviously k and z and all that good stuff, but I don't need to say that. But this is what we've got, right? So we need to ensure that this is the same as, well, what I'm going to write on the left. And what am I going to write on the left? Well, we see that the k plus first derivative is the derivative of the kth derivative. So I see, so on the left side, what I'm going to do is I'm going to write d dx, derivative of the k, well, the derivative of the kth derivative, and therefore the k plus derivative. So the left side is going to be this, the right side is just using the formula, and what we need to show is that this left side is going to turn exactly to this right side, right? Okay, but the derivative of the left side, well, we know the kth derivative is given in the inductive step. Remember, I said the inductive step has to be used somehow in the final step? Well, here it is. Okay, so this is the inductive step, and so in the final step, how does it come into play? So we're going to go d dx, and then a to the k, right, and then sine of ax plus k pi over 2, right? And that's that. And so what's the derivative of this? Remember, a to the k is a constant. So clearly this is going to be equal to, I don't need to be all the way on the left, it's a to the k times cosine of ax plus k pi over 2. K pi over 2 is a constant, but ax, well, that's not quite a constant. Basically, by chain rule, we now need to multiply by the derivative of the inside, which is this. So the derivative of the inside is just a. So I'm going to do times a here, but I could just write k plus 1 here, so I don't have to write the a right there. Okay, so this is the left-hand side, and somehow needs to equal the right-hand side. Anybody's got the magic wand? I do. Remember, we said that sine of theta plus pi over 2 is equal to cosine of theta. By using this, what I could do now is I could write that what I have here is a to the k plus 1 sine of what? Sine of, well, I must call all of this theta, that way I have cosine of theta. So I should write in here sine of theta plus pi over 2. Again, this here is theta. That way we have cosine of theta. Right? We know cosine of theta is sine of theta plus pi over 2. So theta is ax plus k pi over 2. So sine of theta, ax plus k pi over 2 plus pi over 2, that pi over 2, because this is theta, just like that. Okay, if I say that any more times, I'm gonna like jump out the window. It's not that far, so I'll survive and be back with another math video. Okay, probably. all right, but I digress. So what is happening here? Well, we've got sine of, so that part is not so difficult to start. Sine of, okay, ax, and then these two combine, right? In the numerator, I can factor out a pi. And if I do, I'm going to write, if I factor it out and write it on the right, I'm going to have a pi. And then otherwise, I'm going to have a k plus 1 all over 2. Oh, wait, but wait. Guys, Look here. Check. 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 And then, okay. Alright. I'm done.